I'm Kishimoto Haruo, leader of the Fundamentals of Ionic Devices research team. Ionic devices, such as storage batteries and fuel cells, convert electrical energy into chemical energy and vice versa. We study ionic devices on the nanometer order to learn how they work and conduct research to boost their performance. Ionic devices are layers of different materials. On the material surfaces and interfaces, chemical reactions and the movement of ions and electrons convert energy. What are the material surfaces and interfaces like? When a device is operating, what happens at the interfaces? The answers will lead to improved ionic device performance. We produce ionic devices for various purposes and analyze them with cutting-edge measuring equipment. Take a look at our main areas of research.
This is a solid oxide electrolysis cell, SOEC, that we're developing. Here's how we make it. We apply pressure to extract a mold from a uniform mixture of zirconia and other materials. We can make different shapes, like tubes or sheets. We coat it with a ceramic film and sinter it. It's basically the same process as making pottery. When we apply electrodes to this, the SOEC is completed. Let's look at a cross-section diagram. Here, the cathode, electrolyte, and anode are shown in order. Voltage moves electrons from the anode to the cathode. When the cathode is supplied with water and carbon dioxide, its oxide ions are removed, thus generating water and carbon monoxide. The oxide ions pass through the electrolyte. The anode turns the oxide ions into oxygen molecules and electrons. Note the water and carbon monoxide. When they chemically combine, they can make methane and water. Thus, an SOEC is very efficient at converting water and carbon dioxide into various raw materials for making chemical products. We built an experimental system combining an SOEC with a methanation reactor. Existing systems have a conversion efficiency of about 60%. This system can yield a conversion efficiency of nearly 90%. Completing this system will allow us to produce fuel from the CO2 in factory emissions and renewable energy. SOECs can be a useful way to achieve carbon neutrality. We use the latest equipment to measure the devices we make. This is a focused ion beam scanning electron microscope, or FIB-SEM. It's an electron microscope equipped with a device which emits ion beams. This was cut from an SOEC with an ion beam. It shows the cross-section as if it were sliced with a knife. The condition of the SOEC can be observed in minute detail. By switching between the ion beam milling and imaging, we can make a 3D image of the sample's cross-section. This is a secondary ion mass spectrometry microprobe for isotopic and trace element analysis at high spatial resolution, or nanosims. By irradiating with a narrow beam of cesium and oxygen ions, we can extract secondary ions from the sample. The ion beam has a diameter of 50 nanometers. It is possible to irradiate the area to be examined with pinpoint accuracy. It has 7 detectors for detecting 7 secondary ion mass species. As the detector's positions can be precisely controlled, a mass resolution above 6,000 is achieved. The isotopes can also be clearly distinguished.
I was amazed that we could analyze the elemental distribution in our devices in such detail. Up to now, we've been making devices like artisans, but this microscale perspective is incredibly informative.
By accumulating various data, the electrochemical mechanism of the devices becomes clear. We are trying to create a better device by collaboration between those who make devices and those who analyze them. This work is fascinating because the devices are quite challenging to analyze.
We research lithium-ion batteries in this laboratory. This is a sample for measuring lithium-ion batteries at synchrotron radiation facilities such as Spring 8. Lithium-ion batteries are widespread, but there's still much we don't know about them.
We must exhaustively investigate electrolytes and electrodes if we are to dramatically increase lithium-ion batteries' performance. We work with research institutes around the world, like Spring 8 in Japan, to analyze lithium-ion batteries. It's impossible for a single research institute to fully analyze lithium-ion batteries. I think international partnerships will help us go to the next stage.
And in this laboratory, we are developing different types of batteries. This is a redox flow battery, or RFB. Because it can be upsized and has a long lifetime, it's suited to large-scale power storage. Here's how it works. A proton exchange membrane is flanked by 2 types of electrolytic solutions which are circulated. Charge and discharge occur by changing the ion valence and hydrogen-ion exchange. The principle behind the RFB was proposed by NASA in 1974. Around the same time, the Electrotechnical Laboratory, AIST's predecessor, started conducting R&D.
We collaborate with the AIST's Research Institute for Energy Conservation. Redox flow batteries mostly use vanadium, but we're exploring ways to make the batteries with materials that are easier to procure. While carrying on the tradition of redox flow battery research, I want to develop a new type to provide the world with. Ionic devices are fascinating. It is important for research organizations to collaborate to understand their mechanisms and raise their performance. We're looking for new research institutes and companies to do research with. If interested, we would be happy to have you visit. Let's make the Ionic devices of the future together.